Hi, my name is Kimi Okuno from the Institute of Statistical Mathematics, Japan. Today I'm going to talk about an interpretable neural network-based non-proportional odds model for ordinal regression with continuous response. This work is a joint work with Dr. Kazuharu Harada of Tokyo Medical University. At first, I'd like to appreciate Dr. Lucas Cook for his kind cooperation. For instance, at first, he gave us some emails to let us know about the related researches in your groups. The updated version of our archived manuscript now refers the researches of your groups. Also, he arranged today's seminar, so thank you very much for Dr. Cook. We also appreciate Kohei Hattori, Keisuke Yano, Shuichi Kawano, and Kei Hirose for helpful discussions to promote this study. Okay, anyway, let's get started. Okay, firstly, in this slide, I'd like to explain about the purpose of the problem considered in this study. The purpose here is to model the conditional cumulative probability, CCP. Please see the equation here. In this equation, X denotes the covariate and H denotes its response. Then CCP is defined as the probability that the response H is less than or equal to the threshold U when the covariate X is conditioned. As many of you may know, the probability that the H is less than or equal to U is equivalent to 1 minus probability that H is greater than U. So these two probabilities are equivalent. Okay, here I listed some examples of CCP. In this example, we consider the house price in real estate dataset. Covariate X denotes the house age, and the response H denotes the house price. Then we may predict the probability that the house price is less than or equal to $100,000 when the house is 10 years old. Here, the probability is predicted as 0.7. So this is an example of the CCP estimation. And CCP estimation has, kind of constraints. As CCP is a cumulative probability, CCP should be monotone. For instance, if the house age is fixed, then the probability that the house price is less than or equal to $10,000 is less than or equal to the probability of $20,000. So this inequality is obvious from the definition of the underlying cumulative probabilities. So the estimated probability should be monotone as well. So the monotonicity is kind of important properties in this study. And also in this study, we focus on the interaction between the covariate X and the response H. In fact, this study has been studied from the statistical point of view. So our intention is to clarify which of the covariate has a large impact to the response H. For instance, if the house age has a big impact to the change of the house price, we want to detect it. Our ultimate goal is to interpret the interaction between the covariate X and the response H. Okay, this slide shows the outline of this talk. In this talk, I first describe the background. Then I talk about the proposals. And subsequently, I talk about the numerical experiments and conclusions. Maybe let's get started. At first, I'd like to talk about the background. This slide shows the datasets typically considered in the previous studies. Typically, classical ordinal regression considers only the ordinary discrete response. This table shows the examples of such discrete responses. For instance, in the car datasets, there are many datasets of cars. In each data, the covariate represents for each car the level of maintenance, number of doors, number of people who can ride in the car, and so on. And then the response G represents the rating of the car. Actually, some professionals preliminarily evaluated the cars for the response G. And other examples are datasets of heart disease and wine quality and something like that. The important thing here is that typically the number of levels j in the ordinary discrete response is typically less than or equal to 10. So j is not that large in the ordinary regression. Okay, this slide also shows the ordinary continuous responses. For instance, in fuel efficiency datasets, the covariate x represents the horsepower, weight, acceleration, and so on of a car, and the response h represents the fuel efficiency of the car. The fuel efficiency is represented by the miles per gallon. This is a continuous variable. And in housing price datasets, the covariate x represents the house age, distance to the station, and so on of a house, and the response h represents the price of the house. So there are many examples of the ordinary continuous responses as well as the ordinary discrete responses. So these two are examples of the ordinary responses. And then using these responses in classical ordinary regression, the proportional odds model, we denote as POM here, is defined like this. So, okay, and in this model, the cumulative probability is defined as the sigmoid function applied to the linear regression model. Here, the parameter POM model consists of the intercept alpha j and the coefficient vector beta. Then, the likelihood of the POM model is defined like this. The most important point here is that the POM is always monotone as long as the intercept is monotonically increasing. This is because the inner product between beta and the covariate x is independent of j. So if the alpha j is increasing, then the estimated probability is obviously increasing. So we may design increasing alpha j to obtain the monotonicity. As a paper of your group written that the alpha j can be modeled as the sum, like alpha j plus exponential gamma j, alpha j plus the square of gamma j, alpha j plus the absolute value of gamma j, or something like that. So the POM can be monotone very easily. But the coefficient beta is constant here. So this means that the POM is a bit restrictive. It has only a low expressive power. Okay. The problem here is that whether the coefficient beta is really a constant, actually it is widely known that the coefficient is not constant in some situations. For instance, in restaurant ratings, the good hygiene seems more important for expensive restaurants, and actually good wine selection seems more important for expensive restaurants, and so on. In house price evaluation, the impact of the distance to convenience store seems less important for expensive houses, or something like that. So the coefficient beta seems not constant for some practical cases. And there are several related studies in the application fields, like Fries and Williams, or something like that. So to deal with the non-constant coefficients, the non-proportional odds model has been proposed. In this model, the coefficient beta in the POM proportional odds model is simply replaced with the non-constant coefficient beta j. So the coefficient beta is constant in the POM model, but in NPOM, the constant, the coefficient is not constant. The coefficient is beta j here. It depends on the level j. So as you can see in this model, the coefficients vary across the threshold j. So the NPOM has a higher expressive power than POM model. But actually NPOM is usually not monotone. The monotonicity is not guaranteed. In some cases, the probability that the discrete response G is less than j is not smaller than the probability that j is less than j plus 1. This is because even if the intercept alpha j is increasing, the remaining term represented by the inner product between beta j and x is not constant. This term also depends on j in NPM model, so the monotonicity of alpha j easily deteriorates by the second inner product term, this one. So the next problem here is how to guarantee the monotonicity of the linear regression model FJX. Actually, in previous studies, mainly there are three solutions. Okay, the first solution is based on the existing POM. Actually, POM is monotone. So if any POM is sufficiently close to POM, then any POM is also expected to be monotone. So several studies assume that the non-constant coefficient, beta j, this one, is decomposed into the coefficient beta and the deviation delta j and the fluctuation delta j, and penalize delta j by this norm. Okay. In this formulation, as you can see, if the penalty coefficient lambda goes to infinity, then the beta j approaches to the constant coefficient beta. So the NPOM with large lambda is approximated by the POM, and this NPOM is expected to be monotone. But this approach has several problems. For instance, if lambda is small, then the NPOM is still not monotone. And if lambda is large, then the NPOM consequently reduces to this expressive POM. So there is no meaning to use NPOM. And actually, selecting good lambda seems difficult in practice. Now, some packages in several languages heuristically determines the penalty coefficient lambda so as to preserve the monotonicity of NPOM. So there are some problems in these POM-based solutions. Okay, and the second solution is based on the deep neural networks. I refer to several studies of your groups. In these studies, the linear model FJX has been extended to nonlinear models using the deep neural network model, using the deep neural network gamma, this one. For instance, the CI model is defined as the sum of the functions alpha 0x plus the exponential of gamma cx. The second term is obviously increasing with respect to the discrete threshold j. So this model is always monotone and simple enough. But the model is difficult to interpret. This model is designed for the prediction of the cumulative probability. We cannot interpret the interaction between the covariate x and its response by using this model. Okay, and another model is called DCTM model. Actually, this model is a bit complicated. In this model, the coefficients of linear model is defined by the Bernstein-based functions, and DCTM computes the inner product between the coefficient B and the deep neural network output gamma x. By referencing to the previous studies, the sufficient condition for the monotonicity is provided. I think that the Bernstein-based approach is very interesting. And to be honest, I didn't have any idea to use Bernstein functions to guarantee the monotonicity. But this model transforms the covariate x by leveraging the deep neural network gamma x. So consequently, it is still difficult to interpret the relation between the covariate x and its response. So these two models focus more on the prediction than the interpretation. Okay, and the third one is based on the monotone neural networks. There are several neural networks that is guaranteed to be monotone with respect to the parts of the inputs. there are several monotone neural networks listed here. So actually, they are flexible, easy to compute, and they can be used for ordinal regression, but they still lack the interpretability. So these are three solutions for the monotonicity of the NPOM. Okay. So here I'd like to describe the proposals. Okay, our proposal is very simple. Our model called neural network-based NPOM, we denote our model by N3POM. And the N3POM is defined as the sigmoid function applied to the linear model. The linear model is defined by the sum of the function AU and the inner product between BU and the covariate X. Okay. In this model, the function A is defined as a piecewise linear and increasing function, and the BU is defined as a neural network. Here I used one hidden layer perceptron as the function B. Then the functions A and B are explicit enough. The piecewise function can approximate arbitrarily continuous functions. And the neural network can approximate arbitrary continuous functions as well. And in addition, as you can see in this model, the N3POM is interpretable. As you can see in this model, we consider only the interproduct between the coefficient BU and the non-transformed covariate X. So we can see which of the variable in the covariate is important by considering the coefficient BU. Okay, so the problem here is whether the proposed N3POM is monotone or not. And actually, the answer is yes. We provide a sufficient condition to guarantee the monotonicity of the proposed N3POM. Okay, I'd like to describe the monotonicity from here. At first, I'd like to explain the inconvenience rules. The proposition 1 indicates that if N3POM is monotone for any fixed covariate X, then the coefficient function BU should be constant. So this proposition clarifies that the non-proportional models cannot be monotone for entire Euclidean space. And actually, I want to emphasize that this property holds for all the non-proportional models, including all the existing non-proportional models. Although nobody explicitly mentioned, the existing models have the same difficulty so far. But in any case, the N3POM cannot be monotone for entire Euclidean space. So we here instead consider a restricted region defined like this. The set x to eta is defined as the d-dimensional vector whose norm is less than or equal to user specialized parameter eta. Typically, eta is defined by the maximum value of the norms in the training datasets. Okay, then this figure shows the strategy of ours. As you can see in our strategy, we want the proposed N3POM to be monotone for any x in the restricted region x to eta. We are not interested in the outside of the restricted region. So this is our strategy. Okay, here I'd like to show an inequality. Using the symbol rho infinity, then we define an inequality that the minimum slope of the increasing intercept function AU is greater than or equal to the product of eta rho infinity and the function of neural network weights. Then our proposition 2 states that if the inequality, this one, is satisfied, then the proposed N3POM is monotone for any fixed x in the restricted region x to eta. Actually, this proposition can be easily understood. The left-hand side, this one, of the inequality star represents the fluctuation of the intercept function A. On the right-hand side, this one represents the fluctuation of the neural network-based coefficient function BU. So this inequality indicates that the neural network has less fluctuation, has a smaller fluctuation than the intercept function. Also, as you can see, there is an interesting trade-off between eta and the neural network B. This one, eta represents, it roughly represents the area of the restricted region X eta, and the function of the neural network weights roughly represents the fluctuation of the neural network B. So, and the product of these two quantities is upper bounded by the minimum slope of AU. So if eta increases, the fluctuation of neural network should be decreasing. And similarly, if the fluctuation of neural network is increasing, then the eta should be decreasing. So there is an interpretable and interesting trade-off between the parameter eta and the fluctuation of the neural network B. So this is our theoretical results. Okay, so we obtained the sufficient condition. So using this condition, we proposed a monotonicity preserving stochastic algorithm for training the proposed N3 POM. In this algorithm, we first compute a single step of minimatch gradient ascent for training the functions A and B. Then we compute the quantity C, this one. Okay, and replace the neural network weights like this one to satisfy the sufficient condition represented by the inequality star. Then, the monotonicity is certainly guaranteed. Okay, so this slide summarizes the training procedure of N3 POM. In this training, we first input observations, the pairs of continuous response H and the covariate X. Then we first compute the discretized version of the continuous response H. Then we first apply existing NPOM approach to the discretized responses to obtain the discrete coefficients. After that, we initialize the neural network so that the neural net coefficients approximate the existing NPOM outputs. This initialization is like a distillation of the neural network. And subsequently, at last, we compute the proposed MPS algorithm for optimization. Then we output the estimated function A and B, so we can train N3 POM very easily. Okay, from here I'd like to show the results of numerical experiments. At first, I'd like to show the results of synthetic dataset experiments. In this experiment, the true functions of A and B are specified like this. The coefficient function B star depends on the parameters M1 and M2. Then we estimate the coefficient functions by leveraging the proposed N3 POM and existing POM and NPOM. We compute the estimators over 30 experiments, and we took the median of MNC to the true coefficients. Then as you can see, the proposed N3 POM demonstrates the best score. So the synthetic dataset experiments show a kind of consistency of the proposed N3 POM. Okay, so these are the quantitative evaluations. And this slide shows the estimated coefficient functions. In this plot, the gray line shows the true coefficient function, this one, with respect to the changing threshold U. And the blue line shows the proposed N3 POM. And the red line shows existing POM and NPOM. And as you can see, the proposal certainly approximates the true curve. Okay, so the previous slide shows the synthetic dataset experiments. From here, I'd like to show the results of real-world dataset experiments. In these experiments, the covariate xi are normalized. And the response H are affine transformed affine transform to take value and between 1 and 10, we trained the neural network B by repeating 5,000 iterations of MPS algorithm. And to evaluate the sensitivity to the initialization of the optimization, we compute 10 different trials of MPS algorithm with different random seeds. And here I'd like to explain how to interpret the results. As you know, if we apply the logit function to N3POM, then we obtain this quantity inequality. The probability that the response H is greater than U, the probability is expressed as the sum of the function RU and the inner product between the neural network output is U and X and the covariate X. So what I want to say here is if the coefficient S is large here, then the corresponding covariate element is important to increase the response H. So anyway, let's see the results here. This slide shows the results of OutMPG6 datasets. In this dataset, the response shows the fuel efficiency. In the first column, this one, we plotted the PCA plot of the entire covariate X, histogram H, and log likelihood changing along with the MPS algorithm. And as you can see, the log likelihood is certainly increased by the MPS algorithm. The estimated coefficients are shown here. Please look at the second one, this one, the horsepower. In this plot, as you can see, the estimated coefficient is decreasing along with the changing response rate. So the coefficient is decreasing here. This result indicates that for highly efficient cars, meaning that the cars whose MPG miles per gallon is large, for highly efficient cars, the negative effect of horsepower is larger than that of the low efficient cars. And displacement and weight have same tendency. But also, as you can see, regarding the acceleration and model year of the car, the two quantities have higher positive effect for highly efficient cars. Actually, in my opinion, the results are consistent with my intuition. This is the result of OutMPG6 dataset. Okay, and there is a similar dataset called OutMPG8. OutMPG8 consists of the OutMPG6, which I described in the previous slide. And the two additional variables, cylinders and origin, are included in the OutMPG8 dataset. So comparing these two datasets, OutMPG6 and OutMPG8, we can measure the robustness of the proposed approach against the additional variables. And as you can see, the results of OutMPG8 are consistent with the result of OutMPG6. This is because for the displacement, horsepower, and weight, the coefficients are decreasing, and acceleration and model year, the coefficients are increasing. So these tendencies are the same as OutMPG6. So our proposed approach is robust against the additional variables, cylinders, and origin included in the OutMPG8 datasets. Okay, and I also show the results of one more dataset called real SF datasets. In this dataset, there are three covariates called house age, distance to station, and the number of convenience stores. The response is a kind of house price of unit area. Okay, then please look at the first figure, this one. In this figure, the coefficients for the house age is increasing, and also you can see the coefficient reduces to 0. No, the coefficient increases to 0 for expensive houses. And this result indicates that the house age has a negative effect for cheap houses, but the house age does not have strong effect for expensive houses. Of course, I'm not sure the truth, but we can interpret this result. Please look at the bottom figure, this one. In this figure, I plotted the house age and the house price in XY plot. And as you can see, overall, the house age has a negative effect to the house age. House age has a negative effect to the house price. But there are some very expensive but old houses, some expensive but very old houses here, like outliers. So when you focus on the expensive houses colored by the dark blue, then the regression coefficient from the house age to house price becomes nearly zero. It is very interpretable. And also, please look at the second figure, this one. As you can see, the distance to the station has stronger negative effect for expensive houses. And please look at the third figure, this one. The number of convenience store has overall positive effects because the coefficients are all positive here. Okay. And actually, the positive effect of the number of convenience store is decreasing by the house price increases. Actually, I'm not too sure about the housing situation in Europe, but at least in Japan, this tendency is a kind of understandable. In some famous areas of expensive houses in Japan, there is no convenience store at all. The wealthy people usually do not go to the convenience store so often. So the result is very interpretable, at least for me. Okay, I applied the proposed N3POM to several remaining datasets like Boston housing, concrete, and airfoil datasets or something like that. But I skipped the detail in this talk due to the time limitation. Okay, so this slide shows the conclusion. Okay, our preprint has been already uploaded to archive. So if you are interested in this talk, please refer to our archive preprint. And this is contact information. So if you have any question, please contact me. And at last, we again appreciate the Dr. Kohei Hattori, Keisuke Yano, Shuichi Kawano, Kei Hirose, and Lucas Cook for helpful discussions. Anyway, we appreciate your attention. Thank you very much.